know what I found out? I found out that, like, I went back and watched some of my recordings from previous years, that I start literally every lecture with, all right. So you'll, like, every time I record, you're gonna hear me say all right. And I don't know. It'll probably get old, so I apologize. All right, so section 2.4, we are about to dive further into limits. And when we do 2.5, we'll talk about something called continuity, which is a very important concept to calculus. But we need to formalize the idea of a limit first. So when we've looked at limits in the past, like graphical limits, oh yeah, this is also the first installment of what I call Goat's notes. These are Mrs. Gillette's notes. So if you recognize her handwriting, that's why. So this is such a graphical section that I didn't want to remake the graphs using LaTeX. So we're going to use the Goat's notes. All right, well, either way, in the past when we've evaluated limits, the way I introduced it to you guys was I just said, hey, as we pick x values really close to a, and then I would do something like this with my fingers, as we pick x values really close to a, we need to see where our outputs are trending. So what are my outputs getting close to? And it was always close to, like when our limit existed, it was close to some specific value, which we would call L, which was our limit, okay? But mathematicians, they don't like that as an explanation. They wanted a more precise mathematical definition to when a limit exists. So what we're gonna do is we're gonna build that notion of how we determine a limit to exist. Okay, and it starts by doing this, okay? Let's say we have this graph. Now notice this function is defined for everywhere except a, showing that, think about when limits exist in the past, we didn't have to have f of a equaling what L was. It didn't have to be defined at that specific point. It just needed to be defined everywhere else, okay? So I left that point open on purpose, just as a nod to that, okay? So basically what this is having us do is, if I pick some random arbitrary number, let's call it epsilon. So it looks like this. Epsilon is written like this. It's just like a formal Greek E, so you'll see me write it like this. So if I pick some number, let's call it epsilon, and I add it to L, so then L plus epsilon is here and L minus epsilon is there. What it does is it gives me a range of y values, okay? We can correspond those to some x values. So if let's see, what color am I on here? Yeah, let's do red. So if I correspond that to some x values, I'm going to see where those outputs hit my function. So I'm going to say this value here, and then L plus epsilon is here, so I'm going to pick another value right here as well too. Okay? So basically, what we need to be able to do is we need to be able to pick, a span of values such that our L plus epsilon can be mapped to a specific input, or at least a range of inputs into our function. Now we're going to call that, we're going to say this is a plus, we're going to use delta. So this is the Greek letter delta, okay? It's lowercase delta. So then here is going to be a plus, or a minus delta instead of plus. Okay, so a plus delta is here, a minus delta is there, okay? The way a limit works is we get closer and closer and closer to a value. So what we should be able to do is run this iteration again where we pick an epsilon that's even smaller. So let's say L plus epsilon sub 2. And then, this would be L minus epsilon, sub 2. So then my range of y values has gotten smaller, so I should be able to correlate that to an interval of x values, which is also smaller. I should be able to pick a smaller delta, so let's say delta sub 2, a minus delta sub 2, such that those values are smaller as well too, okay? And I can repeat this process until I get increasingly closer to L, okay? And as long as I do that, then as long as I can pick delta values such that, it fits within those confines, then that means my limit exists, okay? If I had a limit that was broken apart, like, a jump discontinuity or something like that, I wouldn't be able to pick values as close as I wanted to L because it wouldn't go to the same value from the left and the right. So by building this model, it allows me to pick values and allows my function to be nice and clean and there's no breaks or anything like that, okay? Now, a couple things that we can observe from this. We can talk about, if I pick like, L plus epsilon, L minus epsilon, my function f of x is just living somewhere in here. It's got to be within that range of values, as well as, my value for just whatever x would be has to be between my deltas as well too. So one observation that we can make is that L minus epsilon is less than f of x, which is less than L plus epsilon. And that only happens when we can do the same thing with our x values. A minus delta is less than x, which is less than a plus delta. So my function f of x lives within that, like my outputs have to live within that range of L and epsilon values. And then my inputs x have to live within the range of a plus delta and a minus delta is basically what that's saying. Okay, but we can clean that up a little bit. Okay, if you notice for our first expression here, I have an L that's common amongst this compound inequality. So I can actually subtract L from each one. And then what that does, it gives me negative epsilon is less than f of x minus L, which is less than epsilon. And you'll see where I'm going with this. I can play the same game with my x values as well too. So that happens when I could subtract a from all my values. So subtract a from each part of that compound inequality. So negative delta is less than x minus a, which is less than positive delta. Now here's a question for you. What type of compound inequality is this? Do you remember from pre-calc last year? What type of compound inequality this represents? Like what conjunction it is? Is it and or? It's and. Good. We can write and compound and inequalities in this way. There's another way that we can rewrite this inequality though. I don't know if you guys remember this, but we can rewrite this inequality using absolute value. So I can actually write it like this. This is equivalent to saying the absolute value of f of x minus L is less than epsilon. Because if you think about going the opposite direction, you can unpack this inequality by putting negative epsilon over here and then writing it as a compound and inequality. But there's a reason why we do this. What does this represent? What does absolute value represent? It does represent a positive number. What practical application does it represent?
How far from zero?
Yeah. What do we call that? Starts with a D.
Distance?
Yeah, distance from zero, how far we are from zero, right? Absolute value is huge because it represents distance. So what we're saying is the distance between our function output and our limit is less than epsilon when I can play the same game with my x values. The distance between x minus a and between x and a, I should say, is less than delta. Okay, but it is going to be greater than zero, so we'll put that greater than zero there. Okay. Now, what we've just done is generated the definition of a limit. Okay. So in order for a limit to exist, those things have to be the case where they have to fit within those confines. How much longer do I have you? Oh, do I have you till 10:15? Oh, whew, we are golden. I honestly thought the bell was going to ring in 2 minutes. So I was like, how am I going to do 2 examples in 2 minutes? So, oh my gosh, I feel like I have a new lease on life now. All right, well, either way, this is the definition you need to remember. This expression down here at the bottom, that is the one that you have to have committed to memory. Okay, will this be on the AP exam? No, it will not be. Okay. But I'm going to have you guys practice with this a little bit this weekend. I'm not going to give you a ton of problems because I get that this is a bit of a abstract concept, but it's a concept worth studying. Okay, so let f of x be defined for all x in some open interval containing the number a, with the possible exception that f of x need not be defined at a. We will write that we have a limit as x goes to a of f of x equals L. If, when given any epsilon greater than 0, we can find a number delta greater than 0 such that the distance between f of x and L is less than epsilon if the distance between x and a is less than some positive number delta. Okay. All right. So that's what you guys have to have committed to memory. Let me show you how we do this with some examples. Okay. All right. So let's say we're given a limit as x goes to 2 of 3x minus 5 equals 1. We want to find delta if we know a specific epsilon equals 0.1. Okay. So when we're given problems like this, most of what we will do is just take what we are given and then plug it into our definition. And then you'll be able to simplify it and get the desired result that we're looking for. Okay. So let's go left to right in our definition and talk about what we have based on what they gave us. Do we know what f of x is? 3x minus 5, right? Do we know what L is? What is it? Noise. Do we know what epsilon is? Yeah, actually in this case they tell us epsilon is equal to 0.1. They don't always tell us epsilon. Sometimes they just leave that arbitrary and open-ended. But in this example, they actually did tell us what epsilon was, okay? We don't know what x is. We're just going to leave that open-ended because that's our independent variable. But do we know what a is? What would a be? Good, Jay. It's going to be our limiting factor. X approaches 2. So a is going to be our value of 2. And then we want to find what delta is. That's what we're searching for. Okay? All right. Blue. Okay, here we go. So let's plug in what we know. Absolute value of f of x, which is 3x minus 5, minus our limiting value 1, is less than epsilon, which we do know, 0.1. When 0 is less than x minus our value for a, which was 2, is less than delta. All right. We have to solve for delta. We want to find what delta is going to be. Okay, that is our goal. All right. Now, there's some simplification that we can do on the left side. So let's do that. I can combine like terms, right? So we get absolute value of 3x minus 6 is less than 0.1. And then I'm just going to rewrite the right side. Even though it's annoying, I'm going to rewrite it each time even though I'm not really doing anything with it. Now it's negative 5 minus 1. We're going further into the negatives. Are you looking right here?
Isn't that a 4?
Where?
Oh. Let's go.
My bad, dude. It's minus L and then absolute value. My boy Max is ready to die on that hill. It looks like a 4. All right. All right, so we have absolute value of 3x minus 6. What do you guys want to do next? Any ideas? Anything else that we can do with the left side? I'll put it this way. The right side you don't normally do anything with. The goal is to try to get the left side to look like the right side. Since we have two absolute value expressions and we want to find what this is, and there's nothing really that I can do with this, the goal is to get my left side to look like my right side, and then whatever value I end up with over here, that's going to tell me what delta is. Okay, so what can I do on the left side? Yeah, since it's in absolute value, we got to be a little careful about how we do it. So what I'm first going to do is I'm going to factor the 3 out. And I can do that because it's positive 3. So I'm going to write it as absolute value of 3 times absolute value of, what would I be left with on the inside? Okay. And then is less than 0.1 when 0 is less than the absolute value of x minus 2, less than delta. You write delta like an 8, except you don't finish it. How do you guys write your 8? Does anybody do like the circle and the circle? That's crazy. I do like one fell swoop. It's like an infinity that's standing up. So how do you write your infinities? Same way, circle in a circle? You do that as one, like, interesting. Okay. All right, well, what can I do with this 3? I can divide both sides by 3 there, right? Absolute value of 3 is 3, so I don't need to be too careful about it anymore. So then I get absolute value of x minus 2 is less than, what is 0.1 divided by 3? I think it's easier to think about it like fractions.
Is it 130?
It's 1/30th, yeah. It'd be 0.03. But I like to think about 0.1 as like 1/10. And then if you're dividing by 3, it's like you're multiplying by a third. So then 1/10 times a third is a 30th. So I'm going to write it as 1/30. When 0 is less than absolute value of x minus 2 is less than delta. And we did it. My left side now looks like my right side. Because I have absolute value of x minus 2. So then what's delta going to equal? Good. And that's my answer. Okay. So most of the problems that I'm going to have you guys practice, most of the exercises, follows this algorithm where you plug in your values and then simplify the left side to make it look like the right side. Okay? Super. Let's do some more. Let's do the same thing except when we keep epsilon an arbitrary value. So it says prove that the limit as x goes to 2 of 3x minus 5 equals 1 for any epsilon greater than 0. There is a delta greater than 0 such that, and we're going to write our definition. Okay. All right, so start by writing the definition. Oops. Less than epsilon when, I forgot the 0. X minus a is less than delta. Sorry, it should be 0 is less than. Forgot that part. All right, let's plug in what we know. F of x is still, again, 3x minus 6. Ooh, yeah, 3x minus 5, my bad. I jumped ahead. 3x minus 5 minus L, which is 1, less than epsilon, which I don't know what it is this time, but that's okay. Really, it shouldn't be when in between. It should be if I'm using the proper definition. So sorry, I need to change that when to an if. 0 is less than x minus a, which again is 2, is less than delta. And we're really going to follow the same process as we did last time, okay? But we're just going to do it in a general sense this time. So I'm going to make it 3x minus 6 less than epsilon if 0 is less than x minus 2, which is less than delta. And I'm going to divide by 3. But I'm going to do it faster this time because we already talked about the logic of pulling the 3 out, the absolute value, and dividing it, okay? So I'm going to say absolute value of x minus 2 is less than, but this time on the right side, I don't have a 0.1. I just have an epsilon. And since I'm dividing it by 3, I'm just going to say it's epsilon over 3. If 0 is less than x minus 2, which is less than delta. Okay. All right. And that's what we got to do. We just got to get to at some point that shows that absolute value of x minus 2 is on both sides, and as long as we have that in both absolute value expressions, then that proves what we want to show. Okay, so we were able to get that. So we're good. So that means that limit exists because we're able to have some sort of epsilon where that distance is less than. So there you go. You don't need to say that delta equals epsilon over 3 for exercises like this. It's just enough to show that these absolute value expressions are the same. Okay? All right, let's do a little more exciting of an example. So our function this time is a rational function, x squared plus 2x minus 8 over x plus 4. And we want to show that that limit as x approaches, is it negative 4? Yep, equals negative 6. Okay. All right, let's plug in what we know. F of x, a little more interesting this time, is x squared plus 2x minus 8 divided by x plus 4. And then minus my limiting factor, or minus L rather, which is minus negative 6, less than epsilon, when 0 is less than x minus my limiting factor, which is negative 4, is less than delta. All right, so again, the goal is to get the absolute value expressions to be the same, and then that will prove that that limit does indeed exist. Okay. All right. What am I going to do on the left side? For sure. How does that factor? Good. X plus 4, x minus 2. By the way, if you haven't already picked up on the fact that when you have a rational expression and they give you a binomial factor, whether it's in the top or the bottom, and you're trying to factor the other part, like the other polynomial, start by testing the factor that they give you on the other side of the fraction. So what I mean by that is, since it's divided by x plus 4, I bet x plus 4 is going to be a factor of the numerator. So it's always a good place to start. Not always the case, but great place to start. Okay, less than epsilon when 0 less than x plus 4 is less than delta. All right, what happens on the left side? Nice. So then we get absolute value of x minus 2 plus 6 less than epsilon when 0 is less than x plus 4, which is less than delta. And we do a very simple combination. So x minus 2 plus 6 is going to give us x plus 4, right?
Yes.
That's what we're after. We want to show that those absolute value expressions are the same. Shoot, I did it again. I don't know why I keep doing that. It should be if, not when. It should be if. You may be asking yourself, what's the difference, Mr. P? Well, it's based on the definition, okay? That part with epsilon only holds true if that part of delta is there. So it should be if in between each time, but not going to be a stickler on that. So, all right? Okay. I haven't settled on which problems I want to give you guys to practice with this weekend. So I'm going to post them to Google Classroom probably during 7th period, which is when my planning period is. So I want to go through and handpick some good problems through the textbook because I didn't dive as deep into this as you can. So I want to make sure the problems that I'm giving you guys are fairly appropriate to what we looked at in class. Okay? Questions there? Okay. I'll grade your quizzes ASAP. And then I'll get them in progress book when I can, but we'll look at them on 2S day. Okay? Hope you enjoy your Labor Day weekend and enjoy your Monday off. Is anybody going to the thing at Bath Elementary? Yeah, cool. That sounds fun. It's like a pep rally for the elementary students or whatever. Is that what's going on? So it's like the cheerleaders, the football players, marching band, right? It's all going down. So cool. 6th period, right? Yeah. 6th and 7th. The kids are still going to be hyped, though, when you guys get there. They're going to lose their mind. Yeah, go for it. Pick a good one, Rossi. All right. I didn't pick one. I never. I don't know what's popular. So I'll have to think of one. Now that I get that this power is at my fingertips, I'll have to pick one and I'll let you know. I'll think about it all weekend.